Hello, everyone. I'm Mihai Budiu. Today, we'll talk about the structure of the open source P416 compiler. So P4, as you may all know, is a programming language for network data planes, and it's evolving. The spec is available online, and anybody can contribute to that too. And we keep in sync with the spec and open source implementation to make sure that we don't write up stuff that wouldn't work. And this presentation is designed to help you modify this open source implementation of the compiler. And there's a set of slides which is much longer and a little more precise. Here, I'm going to simplify things, and it's part of the compiler repository. I'm going to check in those slides there too, probably. They will be posted as well online. So the compiler was designed to support evolving P4 and also to enable commercial entities and the researchers to extend it with multiple backends. And as far as I know, it does support FPGAs, NICs, ASICs, software switches, and a variety of targets. So I think it's been relatively successful in that respect. And this has been done by having an extensible architecture. So we really didn't design for performance necessarily, but we designed for extensibility. So it's easy to add new targets, to extend the language with your own constructs, to add new passes to the compiler, or to add new optimizations. So essentially, what do you need to know? So there's some things I'm not going to teach you. So you need to know C++, and we use the dialect C++ 11, but you don't need to know all of C++. In fact, you need to know a very small subset of C++. We use something called garbage collected C++, which looks much more like Java and increases your programmer productivity significantly. Essentially, you never call delete, so you never have to worry about memory management. You just allocate objects, and when you don't use them, they go away. I'm not going to tell you how to install the compiler sources. They are all available online. The URL was on a previous slide. And I'm not going to tell you anything about your targets. So I'm assuming you want to extend the compiler because you want to target a new device. I can't tell you about that. So you really have to understand your device very well in order to write the compiler extension. Then you have to understand the spec. And the spec, P4 is a simple language, but it still has this very subtle separation between language and architecture. So make sure that you understand how that works and what is part of P4 and what is part of your target specification. What I'm going to tell you about is the last two bullets on this slide, is how the compiler represents programs and how you modify programs using visitors. So I have three pieces in my presentation, and I'm not sure we're going to get through all of them. And by the way, I welcome questions at any time. So if anybody has questions, feel free to interrupt or post a comment in the chat. So I'm going to start by describing the rough compiler architecture. Then we'll talk a little bit about how the programs are represented using something called an IR, or intermediate representation. And then we'll talk about how the IR is manipulated using visitors. So the compiler is divided into three major pieces: the front end, the mid end, and the back end. And interestingly, they all use the same intermediate representation. Many other compilers use different representations across these stages. But in fact, the backend for us is a black box. We have a few backend implementations, but often most of the complexity will be there that is related to your target. The backend is the only one that really has to understand your target very deeply. And that might use a different intermediate representation we don't know anything about. But in the front end, in the mid end, and entering the back end, the same representation is used everywhere. And this is the representation that comes out of the parser. And the separation between front end and mid end and back end is somewhat arbitrary, but in general, the front end should work on all targets. So you don't get to choose what's in the front end. We put that in the compiler. Of course, the compiler being open source, you get to change it if you want it. In the mid end, actually, let me show you the next slide. So the mid end is actually assembled from a collection of pre-built passes. So you get to choose your own mid end for your target. We can give you some passes. You can write more if you want. And the backend is, we don't know much about it. Now, there's three directories in the compiler source tree: front ends, P4, mid end, and backends, and they correspond roughly to these three pieces of the compiler. Now, as I said, the compiler is built out of passes, and there's actually a lot of passes. And some people call this as a Nanopass architecture. because each pass does some very, very little analysis or transformation. So for example, if you run this command line, which uses the P4C eBPF compiler, which is one of the simplest compilers we have, and you compile a very simple program, I counted 378 passes being executed for this simple program. And each pass, if you invoke the compiler with the -v flag, as in this example, it will actually print all the passes that are executed as they are executed. And each pass will be assigned a unique name. So all these passes are not distinct. Some passes will be executed over and over. In fact, type checking makes up maybe about a third of the passes that are executed. Every time we change the program, we re-execute type checking. And because each pass has a unique name, you could also inspect the program after each of these passes. I'll tell you more about that. And
hey, Mihai, can I ask a quick question?
Yeah.
So I know the answer, but I'm asking this sort of to make it public. Could you explain what what expectations are there about certain internal invariants for the IR that need to be maintained as you do, especially transformations of the IR? So you mentioned like type checking needs to be run every time that anything changes because type information is used in various ways. Are there other? Is there a list, or maybe we could develop a list of invariants that are needed, and here's the passes that establish those invariants?
Yeah, so since you have 387 passes, the question is why this order? And some of them, there is a dependency. Some of them should be run in a specific order, but others, we can really freely swap. And some of them you should run multiple times because optimization opportunities could appear again. Some passes do establish invariants for passes that follow them. And these are documented as comments. We don't have any formal language to specify that. So for example, in this slide, I say that P4 evolves in two ways. We extend P4 and we also add new syntax to P4 for things that could already have been done in P4. And let's call that syntactic sugar. And many passes in the front end and some in the mid end actually are responsible for desugaring, replacing this syntactic sugar with lower level constructs, which are less convenient for programmers. Now, obviously, we want to give to the backend a very simple language. So the backend, essentially, you could think of it compiling a much simpler version of P4 than the real full P4 that is in the spec. And that's an invariant that we want to establish. Once you eliminate some construct, we don't want to put them back again. So the program should become simpler and simpler. But in general, we don't have a precise specification of what the ordering should be. And I frankly don't know any compiler that does that. I don't know if that satisfies.
Yeah, fair enough. It would be useful documentation. I think maybe we could develop at some point.
Yeah, so many passes, they would have a precondition that's just as comments, saying, we expect the program to look in this way. And we could say, some of them say this precondition is established by this other pass. We expect it has been run before. But another thing is that, as in many compilers, some passes can be invertible. And some passes do optimizations that are undone by other passes. So the notion of optimization is really cost dependent, and the compiler doesn't have a precise cost model. So for example, common sub-expression elimination and copy propagations undo each other. And you could happily run them forever and never finish. So, and then there's no clear invariant that you want established. It really depends on the context and on the target. Okay, so that's all I had about the compiler structure. Let's move to the IR, which is the intermediate representation. And that's described in a ir.h and IR in the def files. The def files are the most important part of the compiler. So first of all, the intermediate representation is actually very much like a functional program. So first of all, it's a data structure. It's object oriented. So the nodes in the data structure are objects with fields, and it's immutable. Once you build an IR node, you cannot change it. It's also strongly typed. So a node can only point to some other types of nodes. For example, and the structure of the nodes reflects the structure of a P4 program. For example, an expression can only have expression nodes as children. They cannot have declarations because you cannot have a declaration part of an expression in the P4 grammar. And essentially the representation of a program is always a acyclic graph rooted at one node. That one top node is, you should think of it as being in general, it's the program itself. The P4 program represents the whole program, but sometimes you can apply modifications only to trees rooted at nodes internal to this bigger tree. I'll explain. And in this data structure, there's two things which are very subtle. One is that DAGs can be shared. In this picture, for example, C is pointed by both A and B. So there's a sub-DAG rooted at C, which is shared twice. So it's physically shared. These are pointers. And this can be a very subtle source of bugs. You have to understand that you can traverse C either twice or once, depending on what the kind of analysis or optimization you want to do. And the nodes do not have parent pointers, so you cannot go up. You cannot find out who your parents are. And so that's important because C can have any number of parents. So there's no way for C to know who's pointing to it. But when you traverse, you can find out where how you reached C. I'll tell me more about that. And yeah, this IR data structure, you don't have to worry about it too much. You have to understand what it is, but it's manipulated almost exclusively by visitors. So the visitors will traverse these type trees and they will produce type trees. So the structure of the IR is defined in some files with the suffix def from definition. This is essentially a very small language that is a subset of C++. And there's five such files currently for the front end. For example, there's an expression.def which has all the expressions, and I'll show you a snippet of it. You don't worry about it too much. And all the types are in a file of their own. There's a file for P416 which is called v1def. And one thing which is important is that you can add your own def files. So if you write a backend and you want some instruction, for example, I don't know, your target has a built-in hash function or a modulus or some operation that is not supported by the compiler, but you can somehow synthesize it from the program. You can add your own def files, and all the visitors in the front end will work fine with your new classes. You don't have to worry about that. So this is a snippet from expression.def, and you can see it looks a little bit like Java or C++. For example, this says expression is an abstract class. And then we say operation is a subclass of expression. So any operation will be an expression. And an operation has a precedence and has a string representation. These are virtual methods that you'll have to implement. And then we say, there's another abstract class, the unary operations that only have one operand. And this is the operand, they have an expression operand, which is called expr. And then finally, we have a leaf concrete class, like the negation operation. The negation is a unary operation. And here you have to specify the string operation, and it's represented by a minus. And if you look at the real def files, they're only slightly more complicated than this. So in general, they are very, very compact, and they highlight the essentials. For example, you have binary operations. They are subclasses of operation, which are subclasses of expression. And they have two fields, the left and the right operands. And add is an example of a binary operation, which is a plus operation representation as a string, and this is the precedence. So it says a precedence. These are a set of constants defined in a separate file. It's a precedence lower than multiplication, for example. And when you use this class, for example, if you have a node which is a binary operation, you will have 2 pointers, which will point to 2 expression nodes, which will have a concrete type, but we know that they will be expressions. So the type checking will enforce that all times. Does this make sense so far? All right. And
Mihai,
yep.
Just a quick question. So, but the expression and operation are in some other file, right? They're not in expression.def necessarily. Is that correct?
Well, all these classes are in expression.def except the first one, I think.
Okay.
But maybe your question is different.
Yeah. I was just like trying to go through the source and see if I can find the stuff. So
So since this looks like C++, if you're lucky, you feed them to your indexing tool, for example, E tags or VI C tags, it might just index them fine. I don't know if it will succeed, but you might be able to. Yeah.
And so then there is also CPP files, right? So that's something that you get compiled when you compile the
Yeah, so some things you cannot say in def files, and you'll have to implement them in C++.
Okay.
So think of the def files as some kind of headers. In fact, what happens is that the compiler generates C++ out of these def files. We have a separate little compiler that compiles the def files into C++ files. And this is a snippet of the generated code. For example, first of all, everything lives in the IR namespace. So you'd have to use IR when you as a prefix when you refer to any of these classes. And then everything descends from a node, which wasn't specified. See, there's no node in this slide, but everything descends from a node class. And expression is a subclass of node, and operation is a subclass of expression. And the virtual functions get compiled to virtual functions, and the binary operation is a subclass of operation, which has a left and a right. And you see here that the fields are compiled into pointers, and they are const pointers in C++, which means that once you set them, you cannot change them. That's what makes the IR immutable. So you can see how the inheritance in these def files is compiled into a class hierarchy, and the fields are strongly typed, and you cannot, this actually will prevent you from building many kinds of wrong programs. Not all of them, but it's very difficult. For example, an expression will always, a binary operation can only have expressions as arguments. You don't have declarations or tables or attributes or anything else. So the IR might seem daunting. There's actually a lot of classes, a few hundred, but it turns out that the P4 grammar and the IR are very close to each other. So if you understand the P4 language, that's why you have to understand the spec, you will understand almost the entire IR. There's a few classes in the IR that do not correspond to P4 constructs. They are used by the compiler, but most often you won't have to worry about those. For example, some complex types are represented using classes that cannot show up as part of the IR. So these are some important classes. Expression is the base class for all expressions. Type is a base class for all types. Statement is the base class for all statements, like if statement, switch statement, assignment statement, and so on. A declaration is the base class for many declarations. And we also have a type declaration for like variable declarations or control declarations. Type declaration is the base class for all the declarations that are also types. For example, a struct or a header. And there's a few other constructs that are neither of those, like a parser, a table, a controller, and a function. They are more complicated objects that have more fields, but the fields would reflect what you would expect to see in the P4 program. As I said, the node is the base class of the whole hierarchy. And we also have vectors and indexed vectors. So a vector is used, for example, in a block statement. A block statement will have a vector of all the statements or declarations inside. An index vector is like a vector, but it will also keep a hash map for declarations, which allows you to look up a declaration. A declaration is anything that has a name is a declaration. So if you want to find an object by name, then you can ask the index vector to give you the object by name. And the ID stands for an identifier. And the identifiers are like variable names, type names, control names. All these are identifiers, but they are more complicated in the compiler because they remember where they come from in the source, which enables the compiler to give you nice error messages. And they actually have multiple names because the compiler could rename them, but it still remembers where they came from. And sometimes they have a third name, which is the control plane name that you use to address an object. All right. So as I said, the parser is the one that parses P4 programs and converts them into VIR. And the code is in this file. Is front-end parsers P4 parser YPP. That's a YAC or a Bison extension. So you don't have to know too much about Bison. If you know how to read the BNF grammar, you can probably read most of this file. And what is nice about this file is if you look at it, it will tell you how a P4 construct is mapped to an IR node. For example, I have two fragments here. the top one is a production. So the left value equal is followed by an equal sign, followed by an expression, and followed by a semicolon. When the parser parses such fragment of the grammar, what it would build is an assignment statement. And the first object, which is the left value, will become the first argument of, the second argument of the assignment statement, and the expression will become the second argument of the assignment statement. So you can see that if you write equals in your program, you generate an IR node called assignment statement. This @2 stands for the source code position. So the source code position of the assignment statement is the position where the equal sign is, according to this grammar rule. And also the expression production, an expression could be, for example, expression followed by plus sign followed by another expression. You can see that once you see such a production in your grammar, this will generate an add node. So suddenly you have an explanation that the plus converts into an add node in your intermediate representation. And the two expressions, the left one and the right one, are the arguments to the add constructor. Does this make sense? Am I going too fast, too slow?
I'm following, okay.
Actually, maybe I'm a little behind, but it's all right. Now, one thing about the intermediate representation is that we can serialize it in multiple forms. So the IR is really a binary object in memory, but you can serialize it both as a P4 program or as a JSON representation. So we maintain this invariant that all the way to the front end and the mid end, you can convert the IR back to a P4 program. So for example, in this command line, I say after the pass called mid and last, I would like to see the P4 program. And this will actually dump a program that is named from the source. For example, I'm compiling count underscore eBPF. So this will generate a program called count underscore eBPF dash midend underscore 28 underscore mid and last dot P4. So this is the name of the unique pass that is executed corresponding to the mid and last pass. And you can now read this file. It's a normal P4 file. Most often you should just be able to compile it. And you can see how the program looks after that pass has been just applied. So this is actually how most of the debugging and testing is done.
I wanted to jump in with something that might be obvious to most, but JSON is a syntax used for millions of different purposes throughout the world, and it's used for multiple purposes, even within P4 projects. So many people think JSON might be synonymous with BMV2 JSON. That's a BMV2 specific JSON schema. And the JSON format you're talking about here is specific to the IR of P4C.
Yeah, I think I have a slide about that too. Although I don't know if we should spend too much time on that. So another way to learn the IR is essentially to dump it as comments in. So when you dump the P4 program, like using this 2P4 flag, you can add the -v flag, and then the generated code will have comments. These have been slightly rearranged, and these comments actually describe the IR. So for example, you can see here interspersed in black is a P4 program, state IP, it contains a P4.extract statement and a transition statement. And then the comments show you the description of the IR tree indented that represents this program. And if you reformat this IR tree as a tree, it will look like the tree on the right. For example, the parser state is the root of this tree. And then it has two children, the method call statement and the path expression statement, right? The method call expression is the extract, and the path expression is the accept, really. So you see the transition is implicit. There is no transition node. It's just an expression, which is the accept expression. And the method call statement has 3 arguments. Actually, has 3 children. Actually, sorry, I skipped here. The method call statement has a method call expression, which I forgot to depict. And the expression has now 3 fields. It's the method that is called, the types, which are the types in angle brackets, and finally the arguments. So, and so on. You can see the graphical representation on the right corresponds to the comments on the left. So that's another way that you could understand how the programs are represented, by seeing for each P4 program what is IR representation would be. It's a little tedious, but it's not a rocket science. And notice that in this representation, there's numbers after nodes. So these numbers actually are unique IDs. Each node in your IR tree will have a unique ID, which will never be reused during the compilation. And when you create a new node, it will get a new ID. And the compiler, we carefully built it to be deterministic. So if you run your compilation with the same flags multiple times, it will run through exact same code path. And this would enable you to, if you find a bug related to a node, to use this ID in the debugger as a breakpoint. For example, let's say something is wrong in this state. When you see in some pass, something is wrong, like the parser state 58,300 is wrong. So you can put a breakpoint in the constructor of the node, and it's conditional on the ID being 58,300, and that's the program. The compiler will stop when this node is created, and you can see what was happening at that point. All right, so now let me talk about visitors. This is the last part of the presentation. I do have a slide about JSON, but it's a little later. So what is a visitor? It's actually a way of structuring code. It's a relatively new technique. There's a good Wikipedia article about it. Essentially, it means that you can have both objects, which in this class, in this case, are programs represented as IR DAGs, and algorithms that manipulate the objects. And we can separate the two. So you can add new operations, for example, new compiler passes, or you can add new nodes in those trees. You can extend with new syntactic constructs, but they are kind of independent. They don't have to, when you modify one, you don't have to necessarily modify the other. It's actually very spectacular that this could be done. It's not perfect, but it works pretty well. I have a diagram which will explain later about how this works. So the compiler visitors, there's many kinds of visitors. They all are defined in this file called visitor.h. And what do? They are essentially functions. A visitor is essentially, think of it as a function that consumes a rooted DAG. So you take a rooted DAG, a DAG that has only one root node, like node 0 in this picture, and the visitor will transform it to a new rooted DAG that will have a new root node 1. It could possibly leave it unchanged if there's no modifications. And the way this is done is, in C++ code, you can have node 0 be a pointer to the root and a visitor that you declared in some way. I'll show you how you can declare and build visitors. And then to do this transformation, you say just node 0, apply the visitor to node 0. And this gives you node 1, which is the result of the application of the visitor. So visitors are just functions that transform DAGs. Now, there's actually many kinds of visitors. They are all defined in the pass manager header file, but these are the most useful ones. The inspector is a visitor that actually doesn't change your program. I don't know if you heard this. They are forcing us to evacuate the building. See my screen?
Yes.
Yeah, well, take it away.
All right. The weather is great in California. Okay. So we were here. So there's 4 main kinds of visitors. There's a few more, but these are the most useful. The inspector is usually a visitor that actually is not usually, will never change your program, but it can crawl your program and collect information. A transform is a visitor that will generate a new tree out of your program. Then a pass manager is actually a collection of other visitors. You give it a list of visitors and it will run them in sequence over your program. And the pass repeated is like a pass manager, but after it finishes the list, it will run again the visitors from the beginning until the program doesn't change through a complete pass. All right, so the idea is this, that you have 2 types of objects here. We have the classes, the IR classes, like I've showed you: add, subtract, variable declaration, parsers, controls, and so on. These are the columns in this table. And then you have transformations that you want to do to your program. And these are the visitors. So for example, constant folding, type checking, inlining, code generation, all these are the rows of this table. And the visitor pattern allows you to actually build this table and only mark the check boxes that you need. So the base visitor that everybody inherits from needs to know about all the IR classes. But for example, when you do constant folding, you only need to know about some expressions, adding and subtracting and multiplication and stuff like that. But you don't need to worry about variable declarations or parsers or headers or anything like that. So this makes the passes written using visitors be very compact. They usually have only a few lines of code dealing with the classes that they need to deal with. Some visitors are complicated. Inlining is a more complicated visitor, but none of them needs to know everything about everybody. And this is what enables them to also work with backends with IR nodes that they don't know anything about. So that's how you can extend the intermediate representation with new nodes, and the existing visitors will continue to work because they will just leave those trees unchanged. So once you have two visitors, you can chain them. So this is an example where you have a node. Think of the node being the root of this DAG, and then you apply the V1 visitor to get an intermediate tree, and then you apply the V2 visitor to get a final tree. And in C++, this just is a sequence of two visitor applications. And as I said, a pass manager is just a sequence of visitors. And in fact, the compiler frontend, this is an excerpt from the compiler frontend file, is just a sequence, a long sequence of visitors that are applied. For example, the compiler frontend will apply the get v1 model version, then parse annotation bodies, pretty print, validate parse program, and so on. These are all passes that will be run in sequence. And if you look at the front end, what it does, it creates a pass manager, which is a list of passes, and then it says apply here. The program is the input. This P4 program is actually a subclass of the node. It's the root of the IR tree. And you take a program, you apply all these passes essentially in one statement. Now, in general, the visitors operate by modifying subtrees. They don't modify the whole tree. So they will pattern match on a node, and they will generate a new DAG to replace that particular node. For example, in this figure, I'm showing you a DAG rooted at the node. Let's say this is a constant folding visitor, and the node is a plus. And if the operands of the plus are both constants, this will replace this tree with a trivial node, a tree that has only one node. But in general, a visitor will take a rooted DAG and return another rooted DAG. Now, the visitor pattern will actually apply this to a whole tree for you. So in this picture, the blue tree is the blue tree we had on the previous slide, right? So you see blue goes to green. And now this blue tree happens to be a subtree of this big gray input DAG. And it's a subtree, and this orange path is the path of the sequence of nodes you need to traverse from the root to reach this particular subtree. Or one of the sequences, if you remember, there could be multiple paths to reach a specific node. Now, if you remember, the visitor wants to replace the blue subtree with the green subtree, which is rooted at the red node. When you apply the visitor to the green triangle, you get the gray triangle. What you get, it automatically will replace for you, will splice the green tree into the gray tree, and it will leave the blue tree on the side with the path unchanged. So this is actually a technique called copy on write. So the original tree is essentially unchanged. The original tree is still reachable from this root node, from this orange root node on the right. But we have created a copy of the tree, which is rooted at this new yellow node. And this copy of the tree is identical to the original, except it substituted the green for the blue. And both trees exist. So you can continue to compile both of them if you want and analyze them and optimize them. Does this make sense?
Question.
Yeah.
When you go through hundreds of passes, do you end up with quite a bit of in-memory stuff that's, let's say, ancient information, and at the end it just all gets, ignored? Or
yeah. So the question is, what happens to all these tree versions? Indeed, after each pass, you will get a new tree version. And If nobody else is using this rightmost tree, so you don't have any reference to the root of this tree, then this tree will essentially be garbage collected. If you remember, we actually use garbage collected C++. So it just vanishes from memory. You don't have to worry about it. You don't have to delete it.
Thanks.
Someone named Mosin, if you can unmute yourself and ask, go ahead.
Hello, can I ask my question?
Yeah,
Please,
please.
go ahead.
Thank you. I have a question about changing a node in by visitor. Now I'm working on add a new IR to the first IR, and I think I need to and I want to do this by a new pass in frontend, and my question is that I need to add a second IR by adding a new node one by one in the first IR, and there is a simpler way to do this or not. And thank you.
Well, so first of all, if you want to add new types of nodes to the IR, then essentially you just have to create a new def file and or edit the existing ones. So the def files are the ones I shown here, but we have several backends that have their own def files. So you just list those def files, and they will these new IR node types will appear in your IR class hierarchy. So that's how you extend the IR. Now, to write visitors, I haven't shown yet how a visitor manipulates, does pattern matching. So maybe this will answer your question. And if I'm not done answering your question at the end, feel free to post this question in the compiler repository, or we could talk about it next time we have this meeting.
Okay, thank you. I mean, just I want to add two IRs, for example, one IR for UDP, one IR for TCP, and I do not have a new type. I just add two IR by adding nodes in by visitor.
Well, frankly, there's no TCP or UDP in P4. These are actually just data structures that show up in your P4 program. So I don't exactly understand. You want to make them built-in types so you want to extend the language?
For example, I have a code for UDP, processing UDP, and I have another code, another P4 code for processing TCP. And after making IR by compiler, by parser, I want to add a second IR to the first IR. And I want to do it by changing the first IR by visitor. And I want to know that I need to add each node in the second IR by visitor, or I have a simpler way to do it.
So you want to merge two programs?
Yes.
Well, you would have to define a rule on how two programs are merged, because two programs could have conflicts. They could define the same variable, both of them, for example, and what happens in that case. But in general, a P4 program is a sequence of declarations. So by concatenating those two vectors of declarations, you could achieve this effect. So you would have to write a visitor that takes one of the programs as an argument and is applied to the second program.
I would be very grateful if you can explain about type and node class in compiler, because when I work with visitor, I have some confusion about adding node by making a new node or making new type in visitor.
Well, I haven't shown you
for
that,
example,
but this comes next in the talk.
Thank you so much.
All right. So So how do the visitors work? They actually will traverse the tree depth first order. So this is a typical algorithm, one of the first algorithms you learn when you do computer science. You essentially start at the root and you visit the children in order. Given a node, the order you declare fields in the def file is the order the children will be visited. So for example, if you remember an expression had the left and the right, and declared in this order, then the left will be visited before the right. And the visitor will, when visiting a node, the following sequence of operations will be done. The visitor reaches the node and then calls the so-called pre-order function. The pre-order function gives you an opportunity to do some processing, even replace the node if you want. Then you will visit the left child. So look at the diagram on the right. The numbers are the order where the steps are executed. So first you start from the root, then you visit the child, then you visit the left, and then call the pre-order function. They won't let you in. Then you have to visit the left child. Yeah. I'm sorry, I can't help you. All right, so you visit the left child. Then you visit recursively the whole tree rooted there. Then you visit the right child, then you visit the whole subtree. Then you come back to the order, to the root node, and then you call the post order function of the visitor. And after the post order function, you return to the parent. So this is the pseudocode of what a visitor does to each node. And let's see some examples. So for example, this is a visitor. This is a fragment from the strength reduction visitor, which is a visitor that is a transform. So it generates a new tree. And you see this post. So the strength reduction is done as a compiler optimization that is done bottom up. So you first optimize the children of an expression, and then you can optimize the expression itself. And that's why we use the post order. So first we want to optimize all the children. And then once we see what the optimized children are, we can decide what the parent should look like. And this is a declaration of a visitor. You see the strength reduction is a transform, which is a subclass of visitor. And it has, in this case, 5 post order functions. So it knows how to optimize subtractions, additions, shifts left, shift rights, and multiplications. And that's what you have to implement. You'll have to implement those 5 functions. And this visitor doesn't need to know anything about P4 programs, tables, or controls, or parsers, or anything like that. It just looks at expressions. So here's an example of a concrete method from the strength reduction visitor, the one which essentially will optimize the additions. So this is the strength reduction function applied to an addition node. And automatically, this pattern matching step that I explained will apply this to all the addition nodes that appear in your tree. You write for a generic addition node, and it's applied automatically by pattern matching to the whole tree. So we wrote a simple function called is0, which is a helper function, which takes an expression and returns true when the expression is the constant integer 0. And the way we do that is, if the object is of an object of type constant, then we check if the value of the constant is 0. Otherwise, we say it's not the constant 0. So any expression that is a constant and has the value 0 will be returned true. Any other expression will return false. And now the strength reduction essentially checks if the left operand if the right operand of the addition node is 0, then it will return the left operand. And if the left operand is 0, it will return the right operand. Otherwise, it will return the expression unchanged. And in this case, the optimization will essentially splice and remove some part of the tree, but the optimization could return a completely new node. Does this make sense? All right.
Cool.
Okay. Now, one thing you have to understand is that when any visitor visits your node, it doesn't get the real node. It gets a copy of the node. So the compiler will actually clone the node and give you a clone of the node. And if you want to get the original node that was cloned, you have to call this method called getOriginal. And this can trip you up if you're not careful. And this is useful when to know, because sometimes you build a data structure that involves that node. I'll give you some examples later. You have to index in the data structure with the original node, not with the clone. The clone is something fresh that cannot appear in your data structure. Now, there's something called the context. So as I said, the nodes do not have parent pointers. So you cannot find out where a node is in a tree. But when you're being visited, the visitor keeps a context, which essentially is the description of the path from the root to the current node, how you got here. Remember, there can be multiple paths to the current node, but the visitor will tell you which is the current path that is being used to visit you. The node could be visited multiple times with different paths. So this function called getContext essentially will give you a pointer to this data structure, which will tell you how you reach this point. All right, now there's two very useful data structures that many passes will use, and I'll introduce them quickly. One is the reference map. And a reference map essentially ties a name to its declaration. So you can, here's a little fragment here, which there's a constant and a struct and an action that uses some identifiers. So the yellow arrows show you what will be in the reference map. So the reference map, you use it to query using an identifier. It will tell you which is the declaration in the program that declared that identifier. So in the reference map, X will point to the declaration of the constant, and W will point to the argument of the action, the parameter. Sorry, that's a parameter. And in general, an identifier in your program is represented by something called a path, not just an identifier, because we expect to support namespaces, and we use paths to specify an identifier in a namespace. And the reference map can be built by calling this resolve references visitor. The result of executing this visitor is an inspector. It doesn't modify your program, but builds the reference map, which then allows you to then look up identifiers and find out what they are. And this can be very useful because you can find out whether two names represent the same object or not. They are the same object if they point to the same declaration. Is this clear? We only have 5 minutes left, so let me cover the next one. The type map is another data structure which is built by another visitor, which is called type inference visitor. So when you call the type inference visitor, it will populate the type map for you. And the type map for every object that has a type, and many objects have types, it will have these objects point to the actual type that they have. So for the same program fragment as before, X, this constant X, the type map will be populated with a type representing the 8-bit wide integer. And X, the X's type will be this 8-bit wide field. Now, W is an object of type whose type is a structure. So the W name will point to a representation of called type struct, which represents the whole struct and all its fields. You see the type struct, this struct happens to have only one field, which is called S. And the field S also has a type, which is happens to be an 8-bit integer. So that's why the field S also points to the 8-bit integer type. And X here is an 8-bit number. So it represents, it's a variable whose type is an 8-bit value. So that's why X also points to the 8-bit type node. So this is very useful. Many optimizations need to know the types of the objects in order to optimize them properly.
A quick time check here, Mihai. Do you have? Are you near the end, or like I'm perfectly happy if we want to schedule another follow-up to get us through at a more leisurely pace rather than trying to rush to the end.
Well, let's see. So I have 4 more slides.
I mean, if you want, we could just maybe pause there for a quick question and then just schedule another 15 minutes or something for finishing plus some Q&A time later, if that's all right. Or
sure.
Sorry to interrupt.
No problem.
There'll be a lot of Q&A.
Yeah, I suspect.
I like the idea of having another session, and even if there's unstructured time, I think we could potentially identify some open source projects that would be things that a beginner could pull off that don't involve heavy compiler stuff, but use the framework. That would be really cool.
So the 2 slides I had was how do you delete a node? I told you how to replace a node, but not how to delete one, and how to insert new nodes. And that's essentially, and the one about when how you're going to write a backend to generate something different. But in all, I want to say that P4 is a relatively simple language compared to something like Rust or Java. It's a much simpler language, and the front end makes the P4 language even simpler. It will eliminate many of the complicated objects and give you just a subset of P4. And the compiler is very modular and extensible. And as a proof, many backends have been built. We have 6 on the original repository, but there's commercial backends too. So I think you shouldn't be afraid. If you want to tackle this task, it's certainly doable. It's not rocket science. The IR is learnable because it's relatively close to P4 itself. So if you understand the P4 language, you will understand the IR. And most passes are very, very simple and do just one thing. That's how the compiler is built. So it's like the Unix philosophy to build binaries that do only the one thing and chain them is a big pipeline.
I would also recommend, Mihai mentioned GitHub issues on the open source P4C repo. And if you follow pull requests, there's a way to get, watch all issues on P4C. You can probably learn quite a bit from watching Mihai's comments on pull requests that other people are making to enhancements to the compiler too over time.
These days, the number of reviewers is larger, so many people make reviews. Well, more people, not just me, but
yeah. But if it's something you want to get into, that's a good thing to check your knowledge or learn as well. Well, thanks again, Mihai, and I think we will have time even. I think next time. Tomas, I think he said he estimated 30 minutes for his talk, so there's probably going to be 15 minutes in question time left over for both of your talks if you want to maybe finish up the last few slides next time.
Yeah, well, it's much harder to give a fragment of a talk because some people might not have the context.
Well, we are planning to publish this, so and we'll see how soon we can get it published in case anybody missed it or if they want to refresh their memory next time. But thanks again, and I do need to go at the top of the hour here. But if folks want to, if the meeting lasts past me leaving, they can stick around and chat if they want. But thanks again, Mihai, and see you all next time.